conservation of energy. Again, if we neglect friction, wind resistance, we have conservation of energy. We used to say the potential plus the kinetic before equals the potential plus the kinetic after. Well, guess what? We got to include now rotational kinetic energy. So in this example, we have a disk, a solid disk. So this is a disk. It has a mass of, let's say, 1.20 kilogram. Has a radius r of 10 centimeters. And this disk is rolling without slipping. Without slipping, that means we have conservation of energy. Once start to slip, we don't have conservation of energy there. Rolls without slipping. If the linear speed of the disk is rolling like moving this way, I don't know, left, right, whatever direction you want it, it has a velocity, that's linear speed, it's v, not w. It has a velocity of what? 1.41 meters per second. Here's the question. We'll give you actually color parts. Find what? A. Find the translational kinetic energy. And part B, find the rotational kinetic energy maybe we'll add part C to it even. And part C, what should we ask for part C? Let's find the total kinetic energy. Notice I didn't ask you for the potential energy. Why? Because this one's rolling on a flat surface. So there is no change in the kinetic and the potential energy. It's not risen up and down. So let's look at part A. The translational kinetic energy, that's K. We know it's 1/2 mv squared. It's 1/2, we know what the mass, 1.20, the velocity 1.41 squared. And if I get my calculator handy, 0.5 times 1.2 times 1.41 squared. That's equal to 1.193 joules. The rotational kinetic energy, I use Kr. Trying to see what the book used for a symbol, I don't know. It's 1/2 IW squared. Now I got a little problem. I have no idea what I is, and I have no idea what W is. As the wheel rolls on the ground, it looks like it's spinning around this center, around that point in the middle, not on the edge, because if it was spinning around the edge, it will be like this. If this is the edge, the wheel will be going around this, you know? That's not the case. The wheel is spinning like this the whole time, so around the center of that. So that's a solid disk. So I have to go back and see what the equation for a solid disk. It's 1/2 mr squared. So I equals 1/2 mr squared for a solid disk. 1/2, the mass is 1.2, and r is 0.1 squared. 0.006. Now, I also need to know what W is. V equals R times W. V is what? 1.41. R is what? 0.1. Can we get W? W will be 14.1. So once I have these two pieces, can I calculate what the rotational kinetic energy? 1/2 I, 0.006, and W squared, that's 14.1 squared, and for that we got 0.6 joules roughly, or 596 joules if you want to carry 3 decimal places. And part C, what is the total kinetic energy? It's going to be the sum of these two, the translational kinetic energy plus the rotational kinetic energy, which is add the two numbers, 1.193 plus 0.596 equals 1.789. And again, that's joules. Okay. Let's take another example. When my kids were young, the school decided to go to Boston, Science Museum in Boston, take the kids on a trip there to see that. And one of the things they were doing there, the guy had a little ramp like this. And he took a disc, solid disc, and he took a ring, put them side by side on that ramp, and says which one is going to be moving faster when it gets to the bottom? Which one's going to get there faster? The disc or the ring? And people will guess the disc, and he does them. Some people say it's the ring. Then the question became why? Well, the disc is heavier. He puts them on the scale, it's the same mass. Well, the disc is bigger, puts them next to each other, same size. So I couldn't help it. I said to my son, tell him it's the inertia. My son, probably 4th, 5th grade, goes, inertia. The guy said, very good. What is inertia? I don't know, my dad told me to say that. So I'm in trouble now, like, uh-oh. So let's see what happens here if you put a disc versus if you put a ring. Why one will hit the bottom faster than the other? We'll use the same mass and the same radius. So let's look at the first one if I put a solid disc. Let's pick a mass for it. We'll say the mass is what? Pick a number. How big you want that disc?
10 kilograms.
Wow, that's a heavy one, but let's say 10 kilogram. And radius, pick a radius for it.
5.
5 centimeter? 5 meter will be a huge disc.
Yeah.
How about 15 centimeter? More reasonable, you know, like good sized disc. 5 centimeter might be too small. A 5 centimeter disc, well, probably okay. It will be about this big. But by making 15, the edge to edge will be that size. So it's a good size. You know, we get to see it. When you have a lot of people watching, you want to make sure it's visible. And let's give this ramp a height. How high this ramp? Half a meter?
Yeah.
And my question is, when the disc gets to the bottom, here, what's the velocity? Now remember, initially this one is sitting here. So what's the velocity initially on the top? 0. You're going to let go, and your job is to figure out how fast it's moving when it comes down. Assume as it's coming down, it wasn't slipping. If it wasn't slipping, that means we have conservation of energy. if I take the energy at the top, should equal the energy at the bottom. If I use this as reference, the bottom, the ground here, on the top we have potential energy, T for top. We have kinetic energy at the top, we'll calculate that, and we have rotational kinetic energy at the top. The bottom, potential energy at the bottom, kinetic energy at the bottom, rotational kinetic energy at the bottom. And let's see what each one is. What is the potential energy at the top? It's the mass times gravity times height. What is the kinetic energy at the top? 1/2 mv squared. What is the rotational kinetic energy at the top? 1/2 I/W squared at the top. It should equal the potential energy at the bottom. Mass, gravity times height. The bottom height, the top here. Plus the kinetic energy at the bottom, 1/2 the mass times the velocity at the bottom squared. Plus 1/2 I/W squared at the bottom. That's what the rotational is. And let's fill in the blank. At the top, the mass is what? 10 kilogram. Gravity is what? 9.8. And the height was what? 0.5. That number happens to be 49. Kinetic energy, 1/2 times 10. What was the velocity at the top? 0 squared. That's a 0. The rotational kinetic energy, 1/2 I don't know I yet, I'll give you I in a minute. But what is W at the top?
R times V.
Yeah, V is what? Or
0.
It's V over R, but that's okay. 0 over R, which is what? 0. That's a 0. The bottom. What's the potential energy? Mass, 10. Gravity, 9.8. What's the height at the bottom? 0. That's a 0. The kinetic energy, 1/2 times 10 times V squared. We don't know what V, we're looking for it. That's 5V squared. Plus 1/2 I/W squared. So that's what we have so far. Let's clean all the gibberish stuff that I don't need there because it's just clogging this. 49 equals what? 5V squared plus 1/2. But wait a minute, this is a solid disk. Let me look at my cheat sheet. What is the inertia for a solid disk that spins around its center? 1/2 mr squared, right? 1/2 mr squared. So here we go, 49 equals 5V squared plus, let me multiply these three numbers, just these three numbers. 1/2 times 1/2 is what? 1/4 times the 5? 5 over 4, right? which is 1.25. R squared W squared. I wonder why I don't want to multiply these together. How come? I don't want to replace R with 15 centimeter. Why? Because what is V equal to? R times W. So guess what V squared equal to? R squared times what? W squared. So I can replace this one here now by what? By V squared. And I have matching units. And I can solve for V. So 49 equals 5 V squared plus 1.25 V squared. 49 equals 6.25 V squared. V squared equals 49 divided by 6.25, 7.84. And V is going to be the square root of that, which is 2.8 meters per second. Yes?
Back to when we had 1/4.
Yes.
Did you multiply it by 5?
The mass.
Okay.
Don't. 1/2 times 1/2 is 1/4 times the 5. It makes it 5 over 4, which is 1.25. Oh, the mass is 10.
Yeah,
The mass is 10. I'm sorry. Not, what did I say, 5? Yeah, the mass is 10. So what's 1/4? Is that 2.25 or 2.5? The mass is 10. My mistake. What was the 5 then? Nothing was 5?
The height was 5.
The height? Okay.
5.
So something was 5. I knew that. 2.5. So that becomes what? 7.5. And V squared equals what? Sometimes it's better to use a calculator than try to do it in your head.
6.5.
49 divided by 7.5. That's a 6.53. And V will be the square root of that number. 2.56. Now we're going to replace the disk with actually a hoop there, a ring, with the same mass, same radius, and see what the velocity when it gets to the bottom, and who's moving faster.
I mean, isn't that just giving us the...
Velocity when it hits the bottom, how fast it's moving. Yeah.
But that doesn't tell us, like, which one was moving faster?
Well, if you know the velocity when it hits the bottom, you can actually know that distance, knowing the angle, you can calculate how long it took them time-wise and everything.
Oh, okay.
Yep.
I thought from right here, I should be able to tell that. And I was like, yeah.
Well, if they have the same radius and this is moving faster when it gets to the bottom, trust me, this will get there faster, if it has larger velocity. But if you know that distance, you can calculate the time if you want to figure out how long it took them, who was faster technically.
That was just
Yep.
for the one.
Yep. That's for the disk. Now we're going to repeat the problem with the ring now. Same thing, everything the same. This is 0.5 meters. Mass is 10 kilogram. Radius is 15. Initial velocity is 0. But instead of a disk, it's going to be a hoop there. And what's the velocity here when it gets to the bottom? We'll see who's moving faster. And we're going to do the same thing. the potential of the top plus the kinetic energy of the top plus the rotational kinetic energy of the top should equal potential energy of the bottom plus the kinetic energy of the bottom plus the rotational kinetic energy of the bottom. If I use again this as reference. The potential energy of the top, it's the mass, which is what? 10, gravity 9.8, and the height, which is 0.5. So that number is 49, no change. The kinetic energy of the top is 0. It's not moving. 1/2 mv squared. V is 0. The rotational kinetic energy of the top, that's also 0. It's not spinning yet. We get to the bottom. The potential energy of the bottom is 0. Why? The height is 0. The kinetic energy of the bottom, 1/2 the mass, which is 10 times v squared. That's 5v squared. The rotational kinetic energy of the bottom, 1/2. I wrote I instead of 1/2. 1/2 I w squared. 1/2, and let's look at I. I for a hoop there is what? mr squared. Here's a w squared. Doesn't have a half in it. So 49 equals 5v squared plus, what's 1/2 times 10? 5 r squared w squared. Again, I left it r squared w squared. What's r squared times w squared? Isn't that v squared? (49) equals what? 10 v squared. What's v squared equal to? 4.9, which means v equals the square root of 4.9. (2.2). 1 meters per second. The other one was what? 2.56. You start from rest, you travel the same distance, when you get to the bottom, this one is moving faster than that. The disk is moving faster than the ring. If it's the same distance, no slipping, I guarantee you this will hit the bottom before that one. And that's the reason why when you put them side by side, you'll find the disk goes cruising down faster. Now we try to use this concept to cheat and actually use that. Next time you watch bicycle racing on track, they have this short distance on track. Look at the back wheel of the bike. They're solid, no longer the spoke. For that reason. They're a lot faster there. So that's because of inertia there. We'll do another example like that. Then we'll clean house and go to the lab and finish the class upstairs. We had this problem last time. I talked about deadliest catch, and I said you got a pulley spinning there, and you attach the cage to it, and the thing rises. I think we did this example last time. So we have A pulley right there, spinning in this direction. We'll give you a speed in a minute. And you attach a weight to it. And what will happen, the weight will start to move upward. Then it reaches a point, because this has initially spinning there, this will stop spinning. And this is the weight and has a velocity of 0. It's not moving anymore. The question probably, we can calculate how high did it rise before it stopped. Let's give it some numbers. Do you want to give it numbers? You want to give them some numbers? Let's go. Let's give them some numbers. How fast was this spinning? And let's say counterclockwise, spinning this way. W is what? Want to pick a number? 5 rad per second. Okay. And we attach a weight, not too heavy, because if you put too heavy weight, it's not going to go anywhere. So what's the mass of this? What do you want to put here? Half a kilogram? And how high would it go before this one stops? Stop spinning. So I should look at the energy before should equal the energy after. If we assume, again, no skidding there, no slipping, no friction, neglect the wind resistance, we have conservation of energy. If I use this as reference, the initial height, let's find the potential energy. The only thing we have the potential energy of this plus the rotational energy of the pulley there. The pulley was spinning. That's all you got. So what about oh, actually my mistake. That's for this. What about this? Was this moving upward? Plus the kinetic energy of this one. This one was spinning. The minute you hook this one on it, this is going to have initial velocity. We'll figure out what that number is. I have to give you value for R, obviously. I forgot to give you that part. What's the radius here? 10 centimeters? After that, let's look at the potential energy plus the kinetic energy plus the rotational kinetic energy. If I use this as reference, what is my potential energy for the before? If I use this as reference, what's the height? 0. So the potential energy is 0. Kinetic energy due to rotation. I'm assuming that's a solid disk. So it's 1/2 I W squared. The kinetic energy is what? 1/2 mv squared. We'll come back and fill in the values. What's my potential energy here? Mass times gravity times height. What is my kinetic energy? How fast was this block moving at the end? If this one stops spinning, that means this one is not moving. That's 0. And what about this one? What's W if it's not moving? 0. That's also a 0. Because it's not spinning, it stopped. So let's fill in the values. On the right side, the mass is 0.5. Gravity is what? 9.8. The height, which is h. On the left side, 1/2 I. Let me go back to that chart. What is I? I for a solid disk spinning around the center is 1/2 mr squared. Times W squared plus 1/2 mv squared. Let's fill in the blank. Did we give you a mass for the pulley? No. What's the mass for the pulley? Pick a number.
2.5.
2 is good. I don't know much space there. So this will be 1/2 times 1/2. That's the mass of the pulley, which is 2. R is what? 0.1 squared. 1/2 mr squared times W squared, which is 5 squared. So this is the inertia. Plus 1/2. This mass is not for the pulley. This mass is for this one, because this is moving upward. So what's the mass here? 0.5. And what's the velocity of this? We know V equals R times W. R is 0.1. W is 5. What's V? 0.5? Now I just got to plug in the numbers, solve for H. Okay, let's see. Got to keep my eyes open on this one because I'll probably screw things up. 0.5 times 0.5 times 2 times 0.1 squared times 5 squared. This number is 0.125. 0.5 times 0.5 times 0.5 squared. 0.0625. Should be what? 4.9. Thank you. Yep. Every time I try to do without a calculator, I screw things up. 0.1875 should equal 4.9 H. What's the height here? .38 centimeters. .038 meters, which is 3.8 centimeters. So now we can't neglect when something's spinning, we can't neglect it before. It's, oh, don't worry about it. Now we're saying, oh, no, no, no. We got to include that in our problem. It has a rotational kinetic energy. And again, when this is spinning, this has rotational. Well, when this is spinning, this is also moving upward. This has translational kinetic energy. This has rotational kinetic energy. We can calculate V for this if we know what W for that one. Then they stop, so the only thing we have is potential energy here.